Good morning, all of you. Today we will be discussing about the quantum mechanics problem that will be a Dirac delta potential, and we will see how the wave function looks like in this case. So consider the Dirac delta potential as V of x is equal to negative of V naught delta of x minus a. So basically this is an attractive potential given by this negative symbol, and the strength of this Dirac delta potential is given by V naught, and this particular Dirac delta function is situated at x equal to a naught or x equal to a. So this is how the potential looks like. So here at x equal to a you have a negative spike of strength V naught. So any particle which will be coming from left to right, so it will experience this attractive pull. So we will see how the Schrödinger equation is given for this particular potential. So this is the Schrödinger wave equation for any particular potential V of x. So here for x not equal to a, so I am not considering this particular a point, but rather the all other points. So this is region 1 and this is region 2. So I am considering all the region 1 and the region 2. Region 1, so let me define my region 1. So region 1 is x less than a, and my region 2 is x greater than a. So I'm not considering any point, the exact point x equal to a. So for that the potential will be 0. Why? Because at every other point except a, the Dirac delta potential is 0. So this Schrödinger wave equation will become h cut square divided by 2m d square psi by dx square equal to e psi of x. So what I can do, I can write it this in the form of a second order differential equation, dx square plus 2me divided by h cut square psi of x is equal to 0. Okay, so this will be my Schrödinger wave equation. So this is the second order differential equation. So let me call this particular thing as minus k square. So therefore minus k square will be equal to 2em divided by h cut square. Therefore what I can say, k is equal to minus of 2me divided by h cut square and under root. So therefore the solution over this particular equation will be given by m square minus k square or is equal to 0. So therefore the root of this equation will be m equal to plus minus k, and the solution for this second order differential equation will be psi of x equal to a e raised to power plus kx plus b e raised to power minus kx. So this will be our solution. Please note here that what I am considering here, the energy please note that here that I am considering the energies which will lie in this range. So basically this is energy, so this energy is negative. That's why here this under root of this whole thing, this k, its value will be real value. Okay, it won't be a imaginary thing. So don't confuse with this negative sign here. It will be balanced by this negative energy. Okay, so let's try to apply boundary conditions. Let's apply boundary condition to this. So what should be the boundary condition for this particular problem? So at infinity, so basically both side of the infinity, or at both infinities, that is plus minus infinity, this wave function should vanish. What could be the possible value for x equal to, or basically x tending to plus infinity? This psi of x should be 0. So a e raised to power plus k infinity plus b e raised to power minus k infinity should be 0. So this implies that this e raised to power k infinity minus k infinity, it will anyway go to 0, but this thing will diverge. So but we don't want it to diverge, it should be go to 0. So therefore this coefficient a has to be 0 for positive infinity, or what I can say, in x greater than a region. So therefore, or I can say this psi right of x equal to, only b will be there, so b e raised to power minus kx. So this is for x greater than a. So or right, whatever the right of this Dirac delta function. So what will be the this wave function for Dirac delta potential? So now for x tending to minus infinity, so basically what I can write, x tending to minus infinity is equal to a e raised to power plus k minus infinity plus b e raised to power minus k minus infinity. It should be 0. So now if you see here, this term will anyway go to 0 while this term will diverge. So but I don't want it to diverge, so therefore this coefficient b has to be 0 for negative infinity, or what I can say, in x less than a region. So therefore psi L for left region, psi L of x should be equal to b or sorry, a e raised to power plus kx, right, for x less than a. So we can conclude this as, so psi of x should be b e raised to power minus kx for x greater than a, and a e raised to power plus kx for x less than a. So this is our wave function. Now we still need to know about the coefficients a and b. So what we can do, that since at x equal to a, the wave function must be continuous. At x equal to a, the wave function must be continuous. So therefore b e raised to power minus ka should be equal to a e raised to power plus ka. So or what I can say, that b is equal to a e raised to power 2ka. So let us consider this Dirac delta potential is situated at x equal to 0. So in that case, this b should be equal to a, and the wave function will become a e raised to power minus kx and a e raised to power plus kx. So this is for x greater than a, and this will be for x less than a. So this is our wave function for Dirac delta potential. Or in a simpler way, what we can write, this psi of x is equal to a e raised to power minus k mod of x, since mod of x is also given by this function. So here the range of x is from plus infinity to minus infinity. Okay, so this is our wave function for Dirac delta potential. So let's try to plot this function. So if you see here in this in the functional form of this wave function, you can see that it is a exponentially decaying function on both sides of the origin or x. So this is x-axis and this is my psi of x. So at x equal to 0 it has the value of a, this is the peak value is a, and on either side it is exponentially decaying. So this is the name of this wave function is also known as a kink. So at x equal to 0 there is a kink in the wave function, and as x tending to infinity the wave function is vanishing in the both directions. Now notice here that this wave function psi of x is continuous across this whole region. So for x mod of x in between the both infinities, psi of x is continuous. But let's try to find its derivative, and then we will see that the derivative of this function takes a discontinuous jump. Okay, so let me calculate d psi left dx. So in the left region, so basically in the region x less than 0, and this is the region x greater than 0. So in this region my wave function is e raised to power plus kx, right? So its derivative will be a k e raised to power kx, right? Or what I can say, k times psi l, right? Okay, now for x less than 0, so now for x greater than 0, this d psi by dx for this right wave function will be d psi by dx a e raised to power minus kx. So that will be minus k psi of r. Now at x equal to 0, since the wave function is continuous, therefore psi l should be equal to psi of r. Why? Since psi is continuous. So therefore this d psi l by dx minus d psi r by dx, so that will be equal to times k and then psi at x equal to 0, right? So what will be this? So 2k psi at x equal to 0 is nothing, as I told you, it is the value of a. So the a is the normalization constant. So let's try to find this normalization constant also. So the normalization condition says that from minus infinity to plus infinity, basically the whole space, the mod of this psi x, it should give me 1. So here in my case, minus infinity to plus infinity, mod of a e raised to power minus k mod of x, this, and a e raised to power minus k x, so this value should give me 1. So therefore this integral will become minus infinity to plus infinity a square e raised to power minus 2k mod of x dx, and it should be equal to 1. And now notice here, this function is an even function, right? So in that case, this integral, we can write this in the from 0 to infinity limit, and that should be the twice a square e raised to power minus 2k. In place of mod of x, I can simply write x dx equal to 1. So therefore 2a square and integration of e raised to power minus 2kx will give me e raised to power minus 2kx, and then divided by minus 2k, and the limit will be from 0 to infinity, and this should be in 1. Or what I can do is minus 2a square divided by 2k e raised to power minus 2k infinity and minus e raised to power minus 2k 0, that should be 1, and 2 cancels out, and e a square divided by k, so this will be 0 and this will be minus and this will be 1, so this minus minus cancels out, so this will give me 1 equal to 1. So that means this a square, so basically this normalization constant that should be equal to a k, or a should be equal to under root of k. So therefore let's try to write the normalized wave function. So the normalized wave function will look like psi of x equal to under root k e raised to power minus k mod of x. So here x can vary from infinity to minus infinity. Okay. Now let's try to find the value of this k in terms of known parameter. Known parameters such as the strength of the potential, that is V naught. So let's try to write the Schrödinger wave equation for this potential here, but here the range of x is from minus infinity to plus infinity. Here I am not considering, I'm not excluding that particular point x equal to 0. Okay, so let's try to integrate this above Schrödinger wave equation from minus epsilon to plus epsilon with epsilon tending to 0. So what I am considering here in this particular region, so this I can say that this is a minus epsilon and this is a plus epsilon. So in our particular case this a will be 0, so from minus epsilon to plus epsilon. So in that region I am trying to integrate the Schrödinger wave equation. Okay, so what I am trying to do, h square divided by 2m integration from minus epsilon to plus epsilon d square psi divided by dx square. Integration is with respect to dx, then minus v naught is a constant, so I can take it out, minus epsilon to plus epsilon delta of x psi of x integration with respect to x, then integration from minus epsilon to plus epsilon e psi of x and then dx. Okay, now let's try to calculate all these three integrals one by one. So let me first calculate this. Let me call this first integral. So this first integral is nothing but minus epsilon to plus epsilon d square psi by dx square dx. So this I can also write it in the form of d by dx and then d psi by dx psi of x. So from the first principle of derivative, I can write this in the form of d psi by dx minus epsilon to plus epsilon. So this is this internal function will come out, or what I can say, d psi at plus infinity plus epsilon by dx minus d psi by dx at minus epsilon. Note here that this epsilon is tending to 0, and we have calculated, so this is nothing but the jump in the first derivative of the wave function, and we have calculated this in the earlier problem. So this discontinuous jump is nothing but 2k times a is the normalization constant, so this will be 2k a is nothing but under root of k. So this is the first integral. Now let's try to calculate the second integral. So the second integral is minus epsilon to plus epsilon delta of x psi of x dx. So that will be nothing from the property of this direct delta function, that its value is psi at x equal to 0. So psi at x equal to 0 is nothing but a, and a is under root of k. So this is the value of second integral. Let's find the final third integral. So this third integral is from minus epsilon to plus epsilon e psi of x dx. So, and this psi is under root of k e raised to power minus k mod of x dx. So I can write this separately in two limits, from minus epsilon to 0 e raised to power minus plus kx dx plus from 0 to epsilon e raised to power minus kx dx. So, or this will become e under root of k. So here what I'm doing, changing the variable from x to minus of x, then in that case this limit will be starting from 0 to epsilon, and this minus this plus k of x will be minus k of x. So this will become from limits from 0 to epsilon e raised to power minus kx dx plus e raised to power this will remain same dx. Notice here that these two are the same integral, so I can write this in the form of twice 0 to epsilon e raised to power minus kx dx, and if I integrate it, then I will get 2 e under root of k divided by, from here, minus k, and then e raised to power minus k epsilon minus e raised to power minus k times 0. Note here, this epsilon is tending to 0, so this will become 1, and this will also become 1, so this whole integral will become 0. So therefore this third integral will become 0. So therefore what we left with is this plus this, and this will become 0. So minus h square divided by 2m, and then the first integral value is 2k under root k, then minus v naught, and then the second integral is under root of k, it should be 0. So therefore what I can do is I can cancel out this under root k from both sides, and minus to minus, and this k will become minus of v naught into 2m divided by h square, or equal to minus v naught m divided by h square. Here actually I made a mistake, that in this case this discontinuity, so this is from psi l divided by psi x. So basically what I need is at plus epsilon minus d psi epsilon minus dx. So what I need this, and this is a negative of this value, so that will be negative 2ka. So I will correct this. So here this first integral will be a negative sign, with a negative sign. So here what I will get is a extra negative sign here. So this k value will be a positive value. So this will be my k value. So this k is v naught m divided by h square. So let's try to write our wave function in terms of this new function in terms of this known values v naught m. So psi of x will be, it was earlier under root k e raised to power minus k mod of x. So now this will become psi of x will be equal to under root of m v naught divided by h cut e raised to power minus v naught m mod of x and then divided by h cut square. So this is the wave function for Dirac delta potential for the bound state. So this is for bound state wave function. So here E is less than 0, so that the particle is bounded, and this is the wave function in terms of this known parameter v naught, the mass and the mass of the particle. So let's try to find the energy of the particle in this potential. Energy of the particle. So if you remember, initially I have defined my k as under root of negative of 2m divided by h cut square. So I will plug the value of k here. So therefore k was v naught m divided by h cut square, and that should be equal to under root of minus 2m e divided by h cut square. So squaring both sides will give me v naught square m square divided by h cut raised to power 4 equal to minus 2m e divided by h cut square. So if you cancel m and h cut square from both sides, then you will get E as negative v naught square m divided by 2 h cut square. So this is the energy of the particle when it is in the bound state of the Dirac delta potential. And notice here that this is the only bound state energy. Bound state energy possible. So what we can say that therefore there is only one eigenfunction, or basically the wave function for Dirac delta potential. Okay, so let's try to summarize this, that for Dirac delta potential, the potential is given by v of x is equal to minus v naught delta of x. So I am considering the Dirac delta function is situated at x equal to 0, and the wave function psi of x is under root k e raised to power minus k mod of x. Okay, so where this k value is v naught m divided by h cut square. Also this value is also equal to under root of minus 2m e divided by h cut square. So if you compare both these values, then you will get the energy of this Dirac delta potential as minus v naught square m divided by 2h cut square. So this is the summary for this Dirac delta potential. In the next video we will be discussing some problems, some conceptual problems related to Dirac delta potential. Thank you very much for watching this video.